like to, first of all, a few announcements. On Lab 1, any questions about the write-up, which is like due for the first group tomorrow, right? The TAs and I sat down this morning and talked about grading homework 2, and homework 2 is a little bit kind of touchy-feely, right? It's sort of like, design this thing and tell us how you did it. So we thought we'd better put out a point breakdown of how we were going to grade it. And are there any questions on that? I sent it out about 2 hours ago. Basically, we want you to justify how you're going to set up the direct digital synthesis to meet the DTMF guidelines, DTMF specs, and to justify it using knowledge from 2200. Justify it using signal processing. For instance, highest frequency you have to generate is, what is it? 1477. I thought it was 1600, but 1477. So Nyquist says you should be able to run this at 3 kilohertz, right? 3 kilohertz sample rate. Except if you do that and you don't build a very, very good output filter, better than you could possibly actually build, then you won't make the signal to noise spec, or you won't make the harmonic distortion spec on the DTMF. So you have to sample fast enough to make the harmonic distortion spec. So you're going to have to fit this all together to do homework 2. In kicking around the homework 2 sample code, turns out that I linked up to Mead's blog, which describes some of the ways that he used the 12-bit DAC to do sine wave synthesis. He did not, however, use direct digital synthesis. He used an alternative scheme. You can't use his scheme. You have to use direct digital synthesis. And the reason for that is that with DDS, by using a phase accumulator in which you specify an increment, the frequency is directly proportional to the increment you choose, so it's easy to calculate. But more importantly, the density, the error in any frequency you produce is constant, independent of frequency. So DDS is more settable for frequency. You must use DDS. You must not use the scheme that Tamid used for sine wave synthesis, although the code works just fine for the sine waves he chose. Also, Tamid's scheme works by varying the sample rate depending on the sine wave. That means that it is impossible to use a fixed low-pass filter should you decide to use one. Whereas with direct digital synthesis, you choose one single sample rate and stick with it. All right? So you're going to choose a sample rate, you're going to stick with the fixed sample rate, and use a variable increment to change the frequency. Any questions on direct digital synthesis? Is she?
I understand, like, alright,
So what you're asking is, given that you can generate a sine wave at some frequency, how do you know that the noise and the other spectral components are more than 20 dBs attenuated? Is that what you're asking?
Yeah. And I guess related to
Well, okay, so you could write a MATLAB code fairly easily that would simulate, which would generate a sine wave with any number of frequency, of any number of steps on one cycle, and then put it through one of the many FFT routines available in MATLAB. I suggest P. Welsh. I can never remember whether it's CH or SH. Somebody with a laptop open, tell me right now. Tell me. Is it CH or SH? Google. CH. Oh, I got it right. What do you know? P. Welsh has the advantage of doing some averaging and some shaping of the spectrum, so you get a more accurate example. So you could just try different numbers of samples, FFT them using P. Welsh, and measure the ratio of the next highest error harmonic to the harmonic you think you're synthesizing. That would be a very conservative way of doing it. Should take you like 5 minutes to write that code. It's like 3 lines of MATLAB. Or you could look up a paper which tells you the curve. Might be less work to just write the program. What else? Direct digital synthesis, or lab 2. Do you mean direct digital synthesis? So you're gonna ramp up a signal and then ramp it down again. Are you saying you could use that same to get the total harmonic distortion from it? Sure, absolutely could. I believe that you will find. Well, so I suggested one possibility would be a linear ramp. Another is a raised cosine, so it looks like a half a cosine wave, and another might be exponential. I think you will find that as long as this transition is long enough, on the order of several cycles, that you almost can't tell the difference between those in terms of spectrum. There is a difference, but it doesn't sound very different. Again, let me remind you that for the keyboard scanner, I wrote out a state machine. Remember, 4 states with all kinds of arrows between them. I wrote out a state machine which will debounce a 12-key keypad. The pseudocode I linked up is for 1 button only. Do not confuse them. Thinking ahead to lab 3. Oh my God, what am I talking about? Thinking ahead to lab 3, there's a couple of considerations. One was, I was going to have you bust out TV sets and use TV sets, but there's a couple of reasons not to do that. One is, how many of you actually have a television with NTSC input anymore at home? Oh, 4. Okay. So you couldn't test this over fall break, which falls in the middle of this of this, in fact, it falls right at the end of Lab 3. So the people that are on Tuesday of fall break, who have a lab on Tuesday of fall break, are going to have to demo Wednesday morning when they get back. At least they're going to have to demo Wednesday before 4 p.m. So sometime during the day between 9 and 4 p.m. Is that a hardship on somebody? Is there somebody who can't make at least a half an hour between 8 a.m. and 4 p.m. on Wednesday? It's very, very quiet. Yes? Oh, okay. So, Lab 3 is going to be due the week of the 12th of October. And that means that the Tuesday lab will be technically just at the end of spring break. That means that they will demo on Wednesday morning or Wednesday afternoon. And everybody else will demo at the normal time. It is a 3-week lab. It was calculated to be 3 weeks because I know that there's fall break there. But that also means you don't dare delay in starting it. The other thing is, I was going to have you do this on TVs, as I said, and I decided, well, let's just use the TFT display. So instead of using NTSC televisions, you're going to do the video game on the TFT display. You will have to add, just thinking ahead now, you're going to have to add A to D converters so that you can run a paddle position with a trim pot. And you're going to have to, we're going to have to talk about fixed point arithmetic and a bunch of other stuff. Vector dynamics. But the lab documentation is now officially incorrect. I'll fix it, but it's right now it's incorrect. In the lab write-up it says television. You should replace that mentally, shift it out, and put it in TFT. I'll fix the documentation. That's for anybody who's actually like reading Lab 3 early. And then for a final project, we were talking today and decided that if you want to use some other PIC processor besides the MX250, you can. You can use any PIC32 version you want if you buy it yourself. It has to be within budget, and there's no support. So you have to really want to do it. And it's got to be an MX, not a... What's the other one? MX? What's the other one? Huh? There's the PIC32 MX ... MZ, that's right. You can use any of the MX versions you want. The MZ is quite a different architecture. Don't do it. So now that I've overloaded you totally with every lab that we're going to do in the future, let's step back and talk more about Lab 2, which is where we are now. Any questions about keyboard scanning or state machine debouncing? How many people have actually set up the keypad yet? 1 week of a 2-week lab is now gone. Okay. Questions on the keypad, questions on direct digital synthesis, which is what we've talked about so far. The last thing we have to talk about for Lab 2 is serial peripheral interface, SPI. This is one of several industry standards. Standards are good, everybody should have one. One of several industry standards that are meant for on-board, single-board buses. These are meant for small physical scale buses. There's various other schemes that are used. You've probably seen I2C or I squared C, depending on how you like it, how you like to say it. SPI is a full duplex, 3-wire system. Full duplex means it transmits and receives at the same time. I2C is a half duplex. You transmit or receive. Address here is by chip select. I2C is 2-wire. Save a whole pin that way. And the address is on the bus. Then there's various other systems, microwire, QSPI, 1-wire. 1-wire? Well, it turns out it's a asynchronous protocol with bidirectional data and power over the same wire. Very slow, used very rarely. We're going to stick with SPI because it's fast. On this CPU, you can go as high as the system clock, although the particular DAC we are using is limited to 20 megahertz. So the fastest you'll be able to go for this lab is 20 megahertz bit rate. The overall signaling looks something like you drop a chip select line. Dropping the chip select line is going to be a signal from the master to the slave. The master in this case is going to be the PIC32. When you drop the line for the chip select, you start the transaction with that device. At the same time, the PIC32 will be starting to generate a bit clock. This is the clock that has to be less than or equal to 20 megahertz for this lab. And starts to send data out of what is it called on this chip? SDO. Serial data out. You can set on this particular chip, you can set the transaction length, the time to the number of bits set to 8, 16, or 32 bits. For this lab, we're going to set the transaction to 16 bits because that is what is required by the DAC. If you had more than one device connected to the same bus, you'd run the SDO to both of the devices. You would connect both of the devices back to SDI, and with a separate chip select for each external device. We're only going to use one DAC, so you only have to have one chip select for this particular lab. So how fast can you load a 16-bit word? 20 megahertz, 16 bits, sounds like 3/4 of a, 8/10 of a microsecond. So you start the transaction by loading a data register. I'll show you code that does this. I want to talk it through. You start the transaction, you drop the chip select, you load a data register, bits start coming out. It stops sometime later. And generates an interrupt saying that the transaction is complete. So the question I have for you, should you set up an interrupt, start the transaction, go do something else, wait for the transaction to finish and take the interrupt, or should you just wait? The critical thing that you may not know yet is how long does it take to get in and out of an interrupt? If it takes longer to get in and out of an interrupt than it does to just wait, you shouldn't do it. Who wants to guess? Just wait. What else? And you'd be right. It takes about it takes about 3/4 of a microsecond to get in and out of an interrupt. If you jack up if the clock speed a little bit, you may be able to get in and out in as little as 300 nanoseconds, but it's hardly worth it. So, since we're talking about only about 30 or 40 instruction times anyway. So, you're going to start a transaction by dropping the chip select, load the data register with some data, wait for 3/4 of a microsecond, and then check a status bit until it's true, and then go on with what you're doing. It's a very simple protocol. That's all you've got to do on the transmit end is load a register, wait for it to be done. The annoying part of SPI is trying to figure out what the peripheral is going to do with this data. So, if we go to the DTMF dialer lab, we go to the MCP 4822 data sheet. We find out all kinds of interesting things. You should read this data sheet, folks. Underline it. You can simultaneously output both of the. You have to load channel 1 of the DAC, then channel 2 of the DAC separately. Each transaction is 16 bits. It would be nice for some applications to have both voltages appear at the same instant on the I/O pins. You can do that by strobing the LDAC pin, but what we're going to do is just lock LDAC low. And someplace in here, but not here, it says that is legal to do, is to just latch LDAC low. Fast settling time of 4.5 microseconds. That says you probably shouldn't run this faster than 200 kilohertz or so. 50 parts per million per degree C VREF internal. How do they do that? How do they do that? I have no idea. Does anybody know? That's amazingly small temperature coefficient. Single supply operation, all good. Can operate up to 125 degrees C. Don't do that. And it's 12-bit buffered voltage output. Perfect. More importantly, the pinout, LDAC, you're just going to lock low. There's the chip select line, the S clock, the serial data in, which you might guess gets connected to serial data out from the PIC 32. VDD, ground, and then the two analog outputs. What could be simpler? It is, however, worthwhile looking through some of the other data. How much current does it take? Well, half a milliamp, that's not so bad. The 4822 is what we're using. And the INL error. What's INL? DNA, differential nonlinearity error, is only a half of least significant bit. INL error. I don't even know what that means. Huh, should look that up. Internal reference voltage is rather stable. The noise, the output noise, is 200 microvolts peak to peak from 0.1 to 10 hertz. You going to hear that? Yeah. Say again? Because you can load two separate voltage channels simultaneously. I'm sorry, I mean one after the other. So you load channel A with one 16-bit transaction. You bring chip select up. You bring it down again. You load the other channel. You're going to hear this noise? 290 microvolts of noise is actually a fair amount of noise. You going to hear it? Well, there's two reasons why you're not going to hear it. One, your frequency response at 10 hertz is lousy. You might be able to feel it shaking your chest cavity, but you're not going to hear it. Secondly, the speakers we have zero gain at 10 hertz. Or very close to it. All right, so that's not so much to worry about. Output noise density, 1.2 microvolts per square root hertz. So for a bandwidth of 10 kilohertz, the square root of that is 100. So it's about 120 microvolts of broadband noise. And let's say that you have a volt peak-to-peak output, which is about what this thing will do, or 2 volts peak-to-peak output. Then this is 100 microvolts is 10 to the 4th below that, so that's 80 dBs down. That should be okay. So the noise looks okay for audio work. I don't think you're going to hear a lot of shh in the background from this chip. And it's worthwhile going through this just to see what's going on. But the real meat of this, slowly it loads because yeah, serial interface. This is where you really got to read it. And what you're going to find is that there's a set of commands that you need to write to upload this. Mercifully, this has a fairly nice, simple command sequence. You give for the 12-bit DAC, you give it 12 bits of data that will become the voltage, and then 4 bits of control word, which is easy. The first bit is channel 1 or channel 0, or channel 1 or channel 2. The second bit is don't care. The third bit is gain of 1 or gain of 2. I don't think you can use a gain of 2 with the voltages we're doing here. So don't turn that on. And shutdown, you want it in active mode. If you put it in shutdown mode, nothing appears on the output. So you're going to send if you want to load channel 1, or channel, I guess they're calling it channel B here, channel A. If you want to load channel A, you're going to write a 0, a 0, a 0, a 0, a 1, and a 1. And then you have to get the phase of the clock correct. And as I talked about last time, virtually the only way I know how to do this is trial and error. But luckily I got it right on the first try, because it was just like the last one I did. I copied and pasted the code in, and it worked. So I didn't mess with it. Fairly simple interface. But let's talk about any questions on this. But you should go through this. Typical applications, power supply considerations, single supply operation. Make sure that you read this. Should you put a capacitor across the power supply leads? Should you? All right, I like both answers. If it says to, and why not? And the answer is yes. Always, without fail, for every integrated circuit you put on the whiteboard, doesn't matter what it is, put a 0.1 microfarad capacitor between VDD and VSS, as close to the chip as you can. Because all of these integrated circuits that we're using produce fast transitions, logic transitions, which correspond to fast changes in the current requirement of the chip. And even if the power supply lead is that long going to the integrated circuit, or maybe even just across the whiteboard, only like 5 centimeters, it's still a nanohenry or so of series inductance, which sounds like nothing unless dIdt is 10 to the 9th amps per second, in which case you have a 1 volt drop in the power supply. And you have to short out that inductance with a capacitance, or the chip will fail. So always, always with fast logic, or with an op amp, or anything, any integrated circuit you put on the board, put a 0.1 between VDD and VSS and save yourself some tears. Any questions? Let's look at some code. And I put up 2 examples of DAC code here. One is from Tamid's blog, and the other was one I wrote because I can't stand up here and sound like I know what I'm talking about unless I write the code myself. And those of you with good BS detectors will detect when I talk about code I haven't written. But this is mercifully short code. We do the usual setup. I set it up to run at 40 megahertz. Here's a summary of the 4822 control word because I didn't feel like switching back and forth between the editor and another window. Define a control word which is DAC config channel A, which is exactly what I said. It's 0 binary, 0011, and then 12 zeros. So this is, the first bit is, yeah, the second one is, third one is gain, and fourth one is enable. So we're on channel A, gain of 1, enabled. Interrupt service routine in this case, this is where you're going to put direct digital synthesis. What I put in here was just a ramp generator. So this generates a 12-bit long 4096 step ramp at 100 kilohertz. It was easy, therefore, to verify that all the steps are being taken because it took exactly 40.96 milliseconds to execute. And I used, you can use any port pin you want for the chip select. I just used port B bit 0 here, but you're not going to be able to because I think that one is in use for the TFT. You'll have to change that. So we start the transition by doing a clear bits here. We wait for the transmit buffer on SPI2. What's hooked to SPI1? Right, TFT. We wait for the transmit buffer on SPI2 to have a slot. And then we write to SPI2. And what we're going to do is write the config channel plus the DAC data. In other words, that's just the ramp data right there. As soon as we do that right, the transmit starts. You don't have to do any other signal to start the transmit. That is the transmit command. Is that right? Once it's being written, then you just wait for the busy bit to go low and end the transaction by setting bit 0. And you've just sent a value over the DAC. Straightforward. Mercifully straightforward. Any questions? Yes? Oh, okay. So DAC data is an int, 32-bit int. So if it starts at 0, it counts up until it gets to FFF, which is 12 bits of ones. And then the AND, then it overflows to the next bit. The lower 12 bits are 0, and so the next cycle zeros the counter and it starts over again. So this is modulo 12. This is equivalent to a mod 4096 operator, but much faster. Is that enough? Did that answer it or no? Okay, I'm calculating a value, and then I'm ORing it with the control word right here. And that's where it gets put into the channel. The clock, yes. Well, so we have to set up a clock to run this interrupt service routine because, as you can see, this is a timer 2 vector. So in main, we're setting up timer 2 to run at 400 ticks at 40 megahertz. Sounds like 100 kilohertz. Turn on the interrupt flag, turn on the interrupt service routine, and clear the flag as usual. So at this point now, timer 2 is ticking every 400 ticks, and that's what's generating the 100 kilohertz. You, for this lab, are not going to want to go that fast. Probably. That's a small hint. So, any questions now on the interrupt service routine? Well, let's just keep on going down here. So, what we have to do to set up the SPI channel is, first of all, we have to hook the signal SDO2, serial data output 2, through the PPS system. This happens to be PPS group 2. It's mappable to RPB5, among other things, so I chose that. I set up the chip select as an output pin and set it high to begin with. The SPI clock is divider is 2, so the system is running at 20 megahertz. The SPI channel is set up above as channel 2. We open it. We open mode 16 for 16-bit. Do a master enable and do a clock enable reverse, which happened to be the clock phase option, which worked. Try the other clock phases, see what happens. Turn on interrupts, and while we're doing nothing, because for this simple example, everything is happening in the interrupt service routine. It's really easy to set up, folks. Setting up the DAC output should be the least of your problem. However, we're giving you a keypad scanner code. We're giving you DAC output setup code. There's a DDS example. If you cut and paste those all together, you will have nothing. Don't wait. Do not. I've seen this happen before. One person in the group, do the keypad scanner. Yeah, I got the state machines ready to go. Other person in the group is cranking away doing the direct digital synthesis stuff. The day it's due, they merge the two codes. And it fails. Because, inevitably, some variable is shared, or a piece of memory is corrupted because of name overlap. And if you want to modularize things and work on it separately, that's a good scheme, but don't wait till the last day to merge the codes. Any questions on this? SPI is straightforward. It's particularly straightforward for this chip. The chip I was using, the DAC I was using for a couple of years before, was much harder to set up. It had an obscure data command set. But this chip has 3 big advantages. It's 12-bit. That's a lot of accuracy. The command structure is easy, and it's amazingly cheap, which matters when you have to buy 100 of them. That's not saying I want you to throw them in the trash after you get done with this lab, however. They're not that cheap. Questions about this? Questions about Lab 2? Keyboard scanner, direct digital synthesis, DAC output. 3 completely different pieces. They all have to work together. I know it's easy. It's early in the development cycle. Haven't even had the first lab yet of this cycle, except, well, tomorrow night there'll be the first lab of this cycle. Would it be useful for me to open up the lab tomorrow morning? Would anybody appear if I did this? With a deadline a week away, the answer is almost always no. However, if anybody asks, I will open up the lab. Show up. The problem is that 2300 has the room in the afternoon starting at 1:30. And so we can't be in there from after 1 until 4:30. So I have to open in the morning or at noon, but not later than noon. That's the problem with Tuesdays. Otherwise, I'd have a Tuesday afternoon lab rather than a Tuesday night lab. Nobody wants to come in the morning. Okay, that's cool. I'll do something else. But if you change your mind, let me know. I suspect that next week there will be some demand. Did anybody immediately say, oh, boy, I can use any PIC chip we want. I know exactly which one I'm going to do, the MX795. Did anybody think that? Has anybody thought about using a different chip before now? Think carefully if you're going to do that. Some of them have very nice capabilities, but again, there's no support because we're still learning it. 4 minutes, final projects. Any ideas? Peanut butter and jelly sandwich maker? Okay. Is this going to be a Wallace and Gromit kind of thing with, where you unscrew the lid with a big robot hand and a knife comes in and goes whap and smears it? I mean, or is this going to be like syringes preloaded, syringe A with peanut butter, syringe B with jelly onto the bread? It could be fun. Or are you just going to, throw the bread up and hit with a big gob of peanut butter? Now that's a projectile weapon. I won't allow that. A scooper. Oh man. Requires a lot of power to do that, and some precision. Yes. So a self-balancing robot is a generally interesting thing to do. It was relatively hard to do with the Atmel, and I think should be doable with the PIC 32. As always with these things, the larger the moment of inertia, the easier it is to control, because the slower everything is. So putting a lot of mass up high would help. I think it'd be just hilarious to build a telepresence robot with a sense of humor. A sarcastic telepresence robot walks up to you and insults you. Just like being in a faculty meeting. No, it's not that bad, really. So a peanut butter and jelly maker. So the forces required to get the peanut butter out of the jar are fairly high. The forces needed to not tear the bread have to be rather carefully controlled. If you go the syringe route, don't use chunky style. Anything else? A key card what? Oh, a key card mimic. RFID or RFID. If you were to mimic your Cornell card, that could be considered a violation of the Digital Millennium Copyright Act. And you are going to have to justify very, very carefully that this is a good idea, and it is going to have to be approved by the school. I'm willing to try it. I got to tell you, the odds are low. Yes.
This is unrelated to my project. So regarding the no longer NTSC lab, I guess would we be able to put over to NTSC at some point we wanted to?
So for a final project, yeah, for instance, if you wanted to do an NTSC, so just doing an NTSC game as a final project would probably not be accepted, but if you converted it to, say, color, it would be. Or added some interesting hardware for interaction. For instance, one year, group they figured out how to render a 3D maze cheaply on an 8-bit microcontroller. So it was a first-person maze, you walk down a maze. But to go forward, you picked up the television and rotated it forward, right? To turn, you went like this, right? So it was a direct manipulation, shaking the television. That's pretty cool. What a weird idea. I like it. So if you had some particularly interesting way of manipulating the flow of the action, yes. Okay, now being told, any last minute questions, or shall we get out of here? Let's get out of here.